And the next algorithm is the decision tree. It is a tree-shaped prediction model, and the decision is based on the tree. So there is a sequence of questions. Take a look at this example. We start from this root node, and then the first question is, the temperature is temperature greater than 30? If it is yes, then we follow this direction. If it is no, we follow this direction. Then is it rainy? Then if yes, and indoor activity. Otherwise, go to a beach. Okay. So in this case, if temperature is lower than 0, then indoor activity. Otherwise, go to a park. So in our daily lives, we do this a lot, right? So we use a decision tree, and it is a non-metric method. So which means we don't use any distance here. So we don't actually compare the samples based on the distance. We only use these branches, questions and branches, okay? And it can work with nominal data. Nominal data means it's something like a categorical data. Like instead of numbers, we can have some features like a day, like a Monday, Tuesday, Wednesday, etc. So we cannot say Tuesday is greater than Wednesday, or vice versa. Okay, so there's no order in this categorical data, or something like a genre. Okay, is it a horror film? Is it comedy film? And these are not, we cannot compare which one is higher than the other, right? So these kind of data is nominal data or categorical data. So it's discrete without any notion of similarity or order. Okay, so think about this tree, and we can ask something like, is it Monday? Then if it is yes, then we can take a left branch. Otherwise, we can take a right branch, something like that. So decision tree can be applied to this nominal data so easily without any problem. So far, we talked about the distance measures a lot. So whenever we use machine learning algorithms, most of the time we needed to define the dissimilarities. But decision tree is exceptional. We don't need that. And with decision tree, we can do prediction and training. Okay, so first one, prediction is quite simple. Okay, so given a decision tree, then how can we make predictions for new data? So it's simple. The tree is already given, then we can just follow these branches. Okay, we can accept the question, and depending on the answer, then we can follow the branch. That's good. But the training is not as simple. Okay, so given a data set, how can we select a feature and make a branch? So we have to select a feature, and we have to, if it is a continuous variable, then we have to select a feature, and then we have to select the threshold, right? So is it greater than 5 or 7 or 12? So we have to define the threshold too. So this is not as simple. So we're going to talk about this later after this prediction. So first, prediction. Given a trained decision tree, for each data instance we can predict. So on each node, take the branch with the answer. Repeat this setup until the instance arrives at a leaf node. Okay. When the instance arrives at a leaf node, then take the node's decision. And decision could be obtained by majority vote for classification or average value in the node for regression. So after taking branch, okay, let's say this is the leaf node. Then in this leaf node, we have samples. Or when we train with these samples based on the number of the samples in each class, then we can determine this class, this node. Okay, so in the training, in this node we have five circles and 3 triangles. Okay, so in the training, then we can define this leaf node as a circle. And in this case, if we have 2 circles and 3 triangles, then we can define this node as a triangle class. Okay, so in that case, we can just simply follow this flow, and then we can classify the test instance. Okay, and also we can use this for regression, but in that case we can take an average. So in training, in each leaf node we have some samples, and then we can take an average. So let's say if this one is branch, we have lots of samples here, like we have 12 samples, and take an average of these 12 samples. Then let's say this one is 3.5, and for this branch we have 15 samples, and then take an average, and that is 42. Then with each new data sample, we can follow the branch, and if we are here, then we can just simply take a 3.5 as the regression result. Okay, so prediction is quite simple, just to follow the branch. Here is an example. It's a car evaluation data set, and the task is to evaluate if the MPG miles per gallon of a car is good or bad. Okay, so this one is a label. We have 7 features: the number of cylinders and displacement, the horsepower, weight, acceleration, model, year, and maker. So given this, then we have to predict this mile per gallon. Is it good or is it bad? So in the training, yes, definitely we have this target label, but in test, we are going to have only these features. Okay, and then we have to predict this MPG. And let's assume that this decision tree is already trained. Okay, so we're going to talk about the training later. And if this one is given, then okay, the first question is the number of cylinders. Is it 3 or 4, 5, 6, 7? Oh, this is not binary tree. Okay, but usually we will have a binary tree. Okay, so the number of cylinders, and if it is 4, then the next question is maker. Is it America, Asia, Europe? And depending on this maker, then we can find the result. And now new sample is given without the label. Then as I said, okay, so this is new data. Okay, then we just use the same trained model. Okay, so first question is cylinder. It's 4. Okay, and then next question is maker, Asia. Oh, then MPG is good. And another sample, we follow the same rule with the same tree. So the number of cylinders, 6. Oh, it's bad. Okay, so given a trained decision tree and the evaluation, the prediction is quite simple. But the training is not that simple. Okay, so the most common training strategy for a given test has this kind of process. We start from an empty decision tree. So we have just a simple empty root node, and on each node split the set in the node into subsets based on a metric. So we have to find a feature, and then we have to find a threshold. Okay, and then we can split the set. So at this node we have all the samples, and now we have the subset, first subset and second subset here. So this one will be split into these two subsets. And each subset, we do the same thing. We have to find the best feature to split with the threshold. Okay, so we have to repeat on each derived subset in a recursive manner until the subset at the node has all the same value or class. Okay, so this item says we have to keep doing this until this subset has the same class. In this subset, all the samples have the same class. Then this subset is pure, is clean. So whenever we fall into this subset based on this tree, then we can classify without any problem. Because in this subset, all the training samples are in the same class. So when we have a new test sample, then if the new test sample is in this subset, then it can be classified into the same class. Okay, but if we have half and half, or if we have two red class and 3 black class, then still we have to split this node. Okay, and this one is a top-down induction of decision tree. It's kind of greedy algorithm. So from this node, we find the best feature, okay, and then split. And in this node, we find the best feature with a threshold, and then split, So every time we find the best option and then split. That's a greedy algorithm. So it means when we split here, we don't care this node at all. Okay, so every time we find the best option, best strategy. Actually, we have a couple of training algorithms. Okay, so ID3 and C4.4 and CART. So when you read some papers about machine learning or some application of machine learning, then sometimes they say, oh, I used ID3, or oh, we used the C4.5 or CART. It means they used decision tree. Okay, so instead of saying decision tree, sometimes they say CART, C4.5. And it can ID3 can work with multi-way tree as we have seen. And usually people use C4.5 or C5.0 or CART. And the CART is, I think, more popular. I think that's why sklearn uses CART. Okay, so it uses numerical and categorical values. And when we train the decision tree, then we need a kind of metric. So which feature is more important at this moment to split the subset? Okay, so to select one feature out of all the features, by the way, in this decision tree, we use one feature at this moment, and in the next step, we can use the same feature again, right? So at this moment, let's say, oh, is the temperature is greater than 30, and in this branch we can ask like, oh, is the temperature is temperature less than 0? So we can use the same feature again. So we can every time we have to select one feature out of all the features. Okay, so for classification, we minimize gene impurity or maximize information gain. Okay, so roughly speaking, as I said, we're going to use a feature which split the set into a pure class. Okay, when we split the when we split the set in the node, then the left subtree and right subtree, each subtree has the samples in the single class that is pure. Okay, so again, we have samples in this node, and when we use one specific feature and then with a specific threshold, then we can split like this. Then on the left side we have only class 1 sample, and then on the right side we have only class 2 samples. Then this is perfect. But if we use another feature, then when we split, then let's say the split is something like this. Okay, so we have pure subset here, but this subset is not pure because we have class 2 and class 1. So we want to find the best feature to split a subset into a pure subset. Okay, so for classification, the principle is quite simple, right? So we want to split the subset into pure subset. And what about the regression? So we want to minimize the variance or standard deviation in the node. So when we follow the branch, okay, in this node we have lots of samples. Then when we take the variance, then this variance is high. So we have 100 and we have 102, 103, and at the same time we have 3 and 4 and 5. So in this node we have, these are labels, okay? So in this node we have 6 samples, and these samples labels are like this, and when we calculate the variance is quite high. In this case, in the next node, in the next step, we want to split such that 100, 102, 103, and 3, 4, 5. And in this node, the variance is quite small, and in this node, the variance is quite small. Okay, so in this parent node, the variance was quite high. So we want to split this node into these sub-nodes where the variance in each node is small. Okay, if we split this one into like 100 and 102 and 5, here 103 and 4 and 3. So in this case, the variance is quite high. In this case, variance is quite high. So instead of this split, this one is better. Okay, so this is the basic approach for regression. So now let's talk about the Gini impurity, which is used in CART. And Gini impurity measures how often a decision would be incorrect if it was randomly labeled according to the distribution of labels in the subset. And the lower bound is 0 if the set has only one class. Okay, so what does this mean? Okay, so we have a leaf node, and in this leaf node we have 6 orange and 4 apples. Okay, so we have 10 samples in this node. Okay, then when we label these samples randomly, then how often are we gonna be incorrect? So if we randomly select, and if the selection is apple, that's orange, then 60% we're gonna say orange, right? It's random selections. So 60% we're gonna say orange. Then how much percentage we are gonna be incorrect? 40%. So this much we are gonna be incorrect. Also, 40% we are gonna say, oh, this is apple, right? And in this case, we are gonna be incorrect 60%. So in this case, it's a binary binary class problem, so this one and this one, they have the same value. But when we have another class like 5 watermelon, okay, then these numbers are a little complicated. Let's say we have a 5 orange and 4 apple and 1 watermelon, and then 50% we are going to say orange, and then how many times are we going to be incorrect? 50%. So we have to multiply. And then 40% we are going to say apple. In that case, we are going to be wrong 60%. And we're going to say a watermelon for 10%. And then we're going to be wrong 90%. So we have to add all these numbers. That's impurity. Okay, gene impurity. And if we have only one class, if all the samples are in the one class, so in this node we have 10 oranges, okay, then in this case we're gonna say orange 100%. Okay, then how many percentage are we gonna be incorrect? 0%. So when we multiply, then it is a 0. Okay, so how many times can we say orange? This is orange. How many times can we say apple? 0%. In that case, we are gonna be correct because it is orange, but the percentage to say apple is 0. Okay, because we call the label based on this distribution. So if we have the single class in the node, so all the samples are in the same class, then gene impurity will be 0. So that's what this says. So lower bound is 0 if the set has only one class. So this is the direction. So if we increase this gene impurity in the next node, then that's the way to go. That's the way to split the current node. Okay, and if entropy increases in the node, then gene impurity gets higher. You know what I mean by this? If entropy increases in the node, which means the samples are not from the multiple classes. Okay, so we get all the samples from one class, then entropy is the maximum. So entropy and the gene impurity is connected. They are talking about the same kind of things. So that's why in ID3 or C4.5 they use information gain. Okay, so they calculate the decrease in entropy after the data set is split on the feature. So this one is entropy, as you know. Okay, and then information gain is the difference between these two entropies. This one is, okay, so this is our branch. So now let's say we are at this node and we can calculate the entropy at this node. Okay, and then after split, then we can calculate the entropy from here and entropy from here. So we can compare the entropy from here and entropy from here. Okay, then this one is the current entropy, and this one is the entropy after splitting. So we compare, and if we can increase this information gain, that's the better way to split the current node. Okay, so choose the feature with the highest information gain to split. Okay, so usually you are not gonna implement this decision tree training, so you don't have to implement. And actually, in my career, in machine learning career, I never implemented decision tree by myself, but I used decision tree a lot. Okay, even though you don't have to implement this the logic, then when we use a decision tree or random forest, but still you have to understand how these trees are trained. Okay, you have to understand the principle to better use this decision tree.